Hello everyone, my name is Pedram and I'm a professor in data analytics. Welcome to another episode of Deep Learning. All right, let's begin module number 4, Deep Neural Networks. So I guess finally we're getting into the exciting part of the course. So let's begin this. Okay, so we're going to do this module in two parts, two theory part and a Python part. So in part 1, I will cover the basics. We will talk about, for example, what is neuron from scratch, right? We talk about forward propagation, backward propagation. We discuss activation functions. What are they? Why do we need them? We talk about solvers. So this is the basics of the neural networks, right? In part 2, I will talk about more details, for example, what are different regularization techniques, right? So L1, L2 norm, we talk about dropouts, early stopping, data augmentation. So these are different ways of regularization. And we will discuss why we need to do regularization in deep learning as well. And then we talk about different neural network structures. And before going to the Python part, I will quickly walk you through the concepts of tensors, because we're going to use TensorFlow for this course in Python. And we should know what do we mean by tensor, what is the terminology, what do we mean by shape or size of a tensor, and basically what kind of tensor is used for different type of data. For example, how we save an image, how we save a text, how we save time series, things like that in a tensor. What should be the shape of those tensors? Okay, so let's start with the neurons. What are neurons? These are the building blocks of neural networks, right? And well, they were inspired by biological neurons that are found in human body, in human brain, and it is how it started, but as of today, we know that scientists have no clear idea how brain neurons actually work, but this is how this field started, basically trying to mimic something from human brain, right? And the idea is simple, how information is gathered in a human neuron, a human brain neuron, something like this. We have some synapses, the information is collected, and they are summed, or let's say combined at some point, and then at this point there's going to be something done to them, something is going to happen, and then this information is processed and an output is generated. So this is exactly the same thing that we have in a simple neural network, right? So again, analogy is kind of makes sense if you want to think of it this way. We have a bunch of inputs. We call them input layers. We are going to sum them, based on some weights. We're going to assign weights to each of those inputs, and we're going to do a simple sum. This is a sum of all those weights and inputs. And then we're going to do something to them. We're going to talk about this something. For now, let's call it activation function. You'll see what are those activation functions, why do we need them. But in a nutshell, we have to do something to that linear combination of inputs and weights. And then out of that, we are going to pass this output to our output layer, right? So this is what we call output layer. So if we have something as simple as this, we call it, let's say, simple neural networks. But we can stack multiple layers of these neurons, right? So we can have, so let's call this one neuron. We can stack multiple of them in one layer, and we can have also multiple layers, right? So this is what we mean by deep neural network. So a deep neural network, the word deep is coming from the fact that we're stacking multiple of these neurons in one layer, and then on top of that, you're stacking multiple of these layers. Okay, so that's basically in a nutshell what do we mean by deep neural network. Okay, so let's start with a very simple example, right? Consider the housing price prediction, and imagine this black line is the true relationship between price and square feet, right? So this f of x is the true pattern, true relationship between square feet and price, but we know that, in reality, this true pattern is not observable. We're going to add some noise to it, and the goal is to predict this f hat of, let's say, square feet here, right? So our goal is to somehow figure out what is the shape of that f hat of x. What is the pattern between square feet and price, right? So this is a very, very simple example. So how do we approach? If I want to go with a simple linear regression function, what do? I say, okay, so let's write down the price. The price is going to be some weights or some intercept or some bias term, whatever you want to call it, plus some weight multiplied square feet, right? Square feet. And of course, we're going to add some noise. So this is the model. So imagine we're saying, let's work with a parametric model, linear regression form, and something like that, right? So now we can use this model to make some predictions, right? So we can say, okay, so this is the estimated version of the, let's say this is the estimated version of the line. Let's call it price hat. And we have estimated these weights, square feet, and that's it, right? So this is going to be the equation for this line. It means that now we can make some predictions. So for example, if this is the data, so this is the value that the model predicts. If the square feet is this number, this is the value that the model predicts for the price of a house, right? Okay, now let's write it in a neural network kind of graph. No, let's show it that way. So how does it look like? So we can say, okay, we have some weights. I can go ahead and add this number 1 here. So this is our first input. First input is just a number 1 because we need a constant in the model, right? And in deep learning language or machine learning language, we call it bias term, right? So this is our bias term. And then we are going to have, we have x1, and we're going to assign a weight to that x1. So this step is just a simple sum. Let's go ahead and sum it. This is nothing but what we did here. Okay. Now we can go ahead and generate the output right from here, right? So for example, whatever this model is going to do, it's going to generate an output, right? So if W0 is some number, right, and W1 is another number, we can use the input and then make prediction for the house price. Okay. But there's something in between. So this is what we call the activation function, right? So let's write it down, activation. I'm going to show you why do we need activation. We're going to say that let's do something to this linear combination that we have, to this simple sum, in order to make sure that the output is more appropriate, right? So let's say more appropriate. I'm gonna give it meaning to that. So let's think of a very simple example. Imagine I want to make sure that the prices that we are predicting are always positive. Something as simple as that, right? Because right now what we have, if the square feet is, let's say here, and let me do it like this. If the square feet of a house is here, and the model is going to predict something like this, right? So this is what the model is going to predict for this amount of square feet, and it's negative, right? So we know that we don't have a negative price, so that's why we hope that we get something like this. We get something like maybe a curve like this, behave like this, and then when it hit this horizontal axis, it does something like this, right? So how can we do that? And as you can see, I need to add another, let's say, a function to this sum function, right? So let's apply another function to our sum function to make sure that something like this happens. So in order to something like that happen, we can use an activation function called relu, or relu. Okay, if you do that, and then it's going to guarantee that our new, let's say, prediction looks like this yellow shaded area, right? So this was one reason we can do activation function, right? So one simple reason is that we need the activation function, is just to generate positive predictions. But in general, the main reason that we are using these activation functions, we're applying these extra function on top of the sum function, is to take care of the nonlinearity in the data, right? Sometimes the data, and most of the time in deep learning, the data is complex. There are complex patterns in the data, and we have to add nonlinearity components to this simple sum function. And what adds the nonlinearity component to the sum function is with a function called activation function. Let's look into those activation functions in more detail, but before that, let's see what do we call this process going from input to output. Okay. So we call this forward propagation. Forward propagation is the process of calculating the output of a network given an input. So we start from, and as you can see, we go from left to right through a network, right? So we start from input and then we go all the way to the right. And again, the steps are pretty straightforward. As I said, there's an input level. We're going to assign some weights for those inputs. We're going to sum them. We're going to apply that activation to those sum because we want to incorporate nonlinearity, and we're going to generate the output, right? So as I said, the W0 is the bias term, which help us to shift this summation to the left or right. Well, depending on how you're looking at it, you can think of it to up or down, right? So basically, it's going to shift this entire summation to the it's going to move it, right? So this is what's called forward propagation. Now, let's talk about the more formal definition of neurons, actually, at least the deep learning version of that, right? So neurons, they have different names as well. So we call them perceptron, neuron, node, or unit, right? So usually we go with the term neuron in the, or node in the deep learning language. These are the simplest elements or the building blocks in neural networks, as we said, and they're inspired by biological neurons that are found in human brain. Now, I'm going to show you what happens inside these neurons, right? So look at that. We have some predictions at the end of the day. So this is the output layer, right? At the end of the day, we have some predictions. And as we saw in the previous slide, it's coming from the fact that we are adding these weights to the inputs as a linear combination, right? And then on top of that, you're going to add the bias term. So this is what we're doing here, right? And then we're going to apply an activation function. This sigma is our activation function to that simple sum, right? So this happens inside the neuron. So what happens inside the neuron is actually two things. We have two functions there. One is the z function, which is a linear function. The other one is a nonlinear function, which is the activation function. So we can say it like this. The perceptron usually consists of two mathematical functions. The perceptron's linear function z, so we call it perceptron's linear function z, and the nonlinear activation function sigma. So this is the terminology that you should know. But at the end of the day, what happens inside this neuron is very simple. Give me some inputs. I'm going to add some nonlinearity to it, and generate some output. And remember, guys, this output cannot be the final output. It can be simply the output of this neuron. I can add it to the next neuron, to the next layer, and add it to the next layer, and add it to the next layer, right? So the idea is that from each neuron, you're going to get an output. What you want to do with that, you can stack multiple layers, or you can pass it to the final layer. Okay. All right, now let's see what is this perceptron's nonlinear activation function. So as we stated earlier, it's a mathematical function that is applied to the output of each neuron, right? And we mainly use activation function to let the network learn the nonlinearities and complex pattern from the data, right? So this is the main reason that we're applying activation function, because we want to get more accurate prediction. Okay. There are many of these activation functions out there, but let me walk you through to the 4 or 5 most commonly used ones in the literature. So these are the ones that work in practice, right? But again, the list is extensive. You can check out different activation functions on your own. All right, so let's starting with the sigmoid. So sigmoid is actually a logistic function that maps any real value z to a value between 0 and 1. So here's the formula for that. And if you pay attention to this formula, for example, if z is equal to 0, we have 1 divided by 1 plus e to the power of 0, which is 1/2, right? If you send z to infinity, to plus infinity, so what do we get? We get 1 divided by 1 plus e to the power of minus infinity. So this part is 0, so this whole thing is going to go to the number 1. So that's where we are. And if you send z to negative infinity, so what do we get? 1 divided by 1 plus e to the power of minus infinity plus infinity. So 1 divided by infinity, well, it converges to 0, right? So this is where we are. So as you can see, the good thing is that now your transformed version of z is limited. It's between 0 and 1, okay? So we can avoid generating negative numbers like this, like the example in the housing price we see previously. And basically this is between 0 and 1. So we're going to use this sigmoid function, for example, for binary class classification when you're predicting probabilities of a target to be class 0 or 1. And we know that probabilities are between 0 and 1. So that's why a sigmoid function is one of those ones that are mainly used in the output layer for binary class classification. The next one is tanh. So this is the hyperbolic tangent, or tanh for short, function, which is similar to the sigmoid function. If you look at if you just look at the curvature, it's pretty much similar. Actually, it's a transform version of the sigmoid, or they are transform version of each other. Okay, but it maps the inputs values to value between -1 and 1. So now it goes from -1 to 1. It doesn't go from 0 to 1. Actually, this is important because it gives us some symmetricity. You know, it's symmetric between -1 and 1. And we're going to talk about it. When do we prefer tanh compared to sigmoid? So tanh is usually the used in the hidden layers in between, in the middle of the network, right? So we don't use tanh for the output layer. So it's mainly used for the input layer, for the middle layers, right? Hidden layers in between. The next one, which is one of the most widely used and one of the most popular one, is called relu, or people call it the relu. It stands for rectified linear unit. And the relu function is a simple activation function that maps any input values less than 0 to 0 and greater than 0 to itself, right? So if your input is anything less than 0, let's set it 0. If it is anything greater than 0, it's going to be 1 for 1, right? So as you can see, it seems relu activation function is super simple, but surprisingly, it it has been shown that it improves the training speed of the network dramatically, and it simply works, right? So we're going to talk about, for example, when each of these activation functions are going to work, and in practice, which one is working better. But in general, there is no written rule, or there is no the magic to that. You know, sometimes we have to try them all and then see which one is working better. But in practice, again, there are some of them that has been proven that works better than the other one. And maybe the last one that here I want to discuss is leaky relu. And the reason that we're interested in this leaky relu is that maybe it fixed one of the caveats of relu. And that's when look at that, when here for negative values, the relu is generating 0. So it means that the gradient is going to be 0. If I take derivative of this activation function, that gradient is going to be 0. And we know that this is going to be problematic when we are going through the network to do backpropagation. I'm going to talk about the details later on, but for now, let's say, okay, maybe this is a problem that the gradient is 0. How can we fix it? We're going to fix it by something like this. We're going to say that for values less than 0, the activation function is not exactly 0. It's equal to some epsilon, and this epsilon is very, very smaller than 1. Okay, so this is a leaky relu activation function. We can say the leaky relu allows a small gradients when the input is less than 0, rather than sending it to 0, right? So this can be helpful because it can prevent the problem of dying relu. So there is this thing, you might hear it, dying relu problem. And it happens when some of the neurons in the networks become inactive and do not contribute to the output, because simply the gradient has been 0 and they don't get involved in the updating part of the algorithm, right? So maybe leaky relu is going to solve it. But again, in practice, relu works, especially if your network is large enough and you have a large number of neurons, right? Okay, so now let's look into the other activation function, which is called a Softmax, which is simply an extension to the sigmoid activation function. So here's the formula for the Softmax activation function. So as I said earlier, Softmax activation function is a generalization of the sigmoid activation function, and it is usually used for multi-class classification when you have more than 2 classes, right? Because if you have 2 classes, you can do the sigmoid activation function, and if you have multiple class classification, we can use Softmax. So the idea is that it takes a vector of real numbers. So here, for example, we have 1, 2, 3, 4, 5. Now let's say we have 5 class classification problem, and we're going to assign these numbers to probabilities, right? So it's going to take a vector of those real numbers, convert them into probability distribution. So this is what's going to happen using the formula here. So this is a formula, right? And of course, the sum of these probabilities is going to add up to 1. Okay? So for example, if I have, again, 5 class classifications and I want to see and imagine these are real numbers, and at the end of the day, the output of the model is something like this. I know that the probability that this observation belongs to class, let's say 1 is 2%, class 2 90%, class 3 5%, class 4 1%, and class 5 2%. So the output is going to be class 2, okay, because the probability is 90%. All right, so this is Softmax activation function, and again, it's widely used for multi-class classification at the very last layer, which we call it output layer. So the Softmax activation function has several cool properties, and what maybe one of the most important one is that it is differentiable at any point, right? So this differentiability of the activation function is important. It's going to make sure that we are updating weight more smoothly. Okay, and maybe lastly, if you're curious where the name Softmax is coming from, so basically this comes from a form of argmax, right? So we have this idea of argmax. So if I ask you, for example, what is the argmax of this vector? So you're going to say, okay, so I'm going to generate something like this, 0, 1, 0, 0, 0, right? So this is going to be the argmax because this was the maximum and the rest is basically 0, right? So softmax, we call it softmax because it's a soft version of argmax. It's not going to assign these ones 0, 1. It's basically give them some numbers between 0, 1. So this is where the name softmax is coming from. Okay, now the question is which activation function, right? So there's no right answer, but we know that this is fact. The choice of activation function can have a significant impact on the performance of the neural network. In general, it is recommended to try different activation functions and maybe compare the performance and find the one that works best for a particular problem, right? So it depends, data set by data set, you might end up finding some activation functions better than the other ones, right? But there are some general rules and facts maybe that we can refer to. So here, for example, let's see, what do we have? We have sigmoid activation function, we have tanh activation function, and we have relu, right? So the blue one is the function itself, and the purple ones are the derivatives, right? So I want you to pay attention to the derivative for sigmoid and tanh, especially for extreme values, it's very close to 0. Okay, so, oops, sorry, not this one. The derivative for tanh is close to 0 here. Here, the derivative is close to 0. And of course, for relu, the derivative for when value of z is less than 0, it's literally 0, right? So this is not necessarily good because we know that when we're updating the weights in the networks, when the gradient is 0, we have this problem of diminishing gradient, and the idea is that those observations don't get a chance to get updated properly in the networks, right? So maybe that's one of the downsides of both sigmoid and tanh. And so let's talk about them. Okay. So for hidden layers, almost always tanh is better than sigmoid, okay? Because it centers the data for the next layer. So as you can see, here the tanh is centering the data between -1 and 1 and send it to the next layer. However, sigmoid is not symmetric. It's make the data between 0 and 1 and send it to the network. It really, again, these are very subjective. It really doesn't matter because if you're doing, for example, batch normalization, it's going to take care of these kind of problems in the middle of the network. We're going to talk about the idea of batch normalization in the right time. Okay, so maybe that's one point I need you to remember. Another one is that, again, the downside of both sigmoid and tanh is that the gradient is very small for extreme values. And as we said, we talked about it, when the weights are being updated, these observations are not going to be paid attention as much as they needed. So that's another thing. In practice, relu works maybe best or better compared to sigmoid or tanh for hidden layers, right? So for hidden layers, we can almost always use relu. I personally, I will never use sigmoid for the hidden layers because relu is just basically working better. And we know that, so for example, leaky relu might work better. You might think that it might work better than relu, but if you have enough number of hidden layers, it has been shown that relu is just fine, right? So maybe the takeaway from this slide is that for hidden layers, always use relu, and for final layers, depending on the type of the problem. If it is binary class classification, you can do sigmoid. If it is multi-class classification, you can do the Softmax. Okay, and if it's a regression problem, again, we're going to talk about them in the Python part in more details, but you can even do linear activation function if you don't want to use relu. But usually, if it is regression, you can simply use relu for the activation function in the last layer as well. All right. Now let's look at the numerical example for a sigmoid activation function that we are applying it to a binary class classification, right? So imagine we have two class classification at the end of the day. We want to see if something is class 0 versus class 1, or we can call it class blue versus class green. Okay, we want to see what is exactly this activation sigmoid activation function doing, or what it is actually visually, right? So imagine we throw the data at a network, and the network told us these are the optimal weights. So your bias term is 1, your weight 1 is 3, your weight 2 is -2, and that's it. Go ahead and make some predictions, right? So again, these are the weights, and we're going to make some predictions. So again, this is very simple. At the end of the day, we're going to have 1 plus 3x1 minus 2x2, right? So this is the linear part of the perceptron. So remember, this is our perceptron. It's going to have two mathematical formula, a linear function and a nonlinear function. So the linear function is this part. So let me use yellow. So this is a linear part, right? And as you can see, this is just a line in 2D dimension, right? So I can simply visualize it, right? So if I have, for example, x1 here and x2 here, I can plot this line of 1 plus 3x1 minus 2x2 is equal to 0, right? So this is the line. So this is our line, okay? Now I'm going to pass this to an activation function here, namely our sigmoid activation function, right? So this is our sigmoid activation function. So this means that if I go ahead to, for example, say I have an observation here and I have an observation here, okay? If I go ahead and apply the activation function, it's going to give me something like this. So for example, this is a point -3 and 1, right? And I'm going to apply the activation function to our linear function. So what do I get? Remember, the sigmoid is going to give us something like this. 1 divided by 1 plus e to the power of minus our z function. So what is the z function here? 1 plus 3x1 minus 2x2. Okay, let's go ahead and replace x1 and x2 with these numbers, no, -3 and 1. So what do I get? 1 divided by 1 plus e to the power of minus, so 1 plus 3x1, which is -3, so it's -9, and minus 2x2, which is -2, right? So if I'm not making a mistake, so I get -10 here. So our z is negative, and then 1 divided by 1 plus something, and this is going to be a number less than 0.5. So we have 1 divided by 1 plus e to the power of plus 10. So this is less than 0.5. Okay, so that's what we're getting here. And now if I apply this number, you can go ahead and double check, do the math. So when x1 is equal to 2 and x2 is equal to -1, you can check that you will get, and if you apply the sigmoid activation function, you will get a number greater than 0.5. And if your, for example, cutoff point in your binary class classification is 50%, then this is going to be one class, let's say class 1, this is going to be another class, class 0, right? So again, this is your sigmoid activation function, and imagine this is 0.5, and if your cutoff, well, I have to be more careful, this is something like this. If your cutoff is 50%, then if the value for the activation function is greater than 50%, call it class 1, less than 50%, call it class 0. Okay, this is exactly what we're seeing in 2D, two-dimensional visualization. Hopefully that helps to help you understand visually what these activation functions are doing under the hood. Okay, now let's talk about why do we need non-linear activation function? Because remember, we can have linear activation function, right? So if you don't apply, so for example, if you apply nothing, just a linear function to your z, it's this sigma z, and if sigma is linear, you get a linear function, right? So why do we need to go beyond that? Why do we need to do some non-linear activation function? So if you use linear activation function, then the neural network will always output a linear function of the inputs, regardless of how many neurons you have, how many hidden layers you have. If you apply linear function to a linear function to a linear function to a linear function, the output is linear, right? So you're not able to capture that nonlinearity in the data at all, right? If you use the linear activation function. So let me show you a visualization. So we know that linear activation functions produce a linear decision boundary. So this is our decision boundary. Let me actually right here. This is a decision boundary. And so basically this says that this is a, let's say, two-class classification. Anything to the left is class red, anything to the right is class green in this example. But as you can see, this data is showing very complex pattern. It is nonlinear by any sense, right? So we have this weird kind of nonlinearity going on in the data. So how can we capture a decision boundary like this? If you want to capture like this, we have to use nonlinear activation functions. So nonlinear activation functions are going to help us to approximate the complex pattern in the data and come up with nonlinear decision boundaries in this example. Okay, so now let's look into the next topic, which is building a neural network. So a neural network is a type of machine learning model that is composed of layers of interconnected neurons which process and transmit information, right? So here, for example, in this, we have 3 neurons and one hidden layer, one input layer. These are the inputs and this is your output, right? So in this example, we have 3 neurons, one input layer, one output layer, and one hidden layer, right? So each neuron receives the inputs from other neurons. So for example, this is receiving input from the input layer, process it with using nonlinear activation function. Remember, inside each neuron, there's these two components, a linear component, which is a simple sum, and a nonlinear activation function, right? And then transmit the output to the other neurons in the next layer. So here, the next layer is output layer, and it's going to send the output of a neuron to the next one. You can think of another hidden layer in between, but let's keep things simple, right? The output of the final layer is your prediction, right? It's the prediction made by the neural network. So this is your y hat. Okay. Now, if you have one neuron at the end, if you have, for example, at the output layer, you can have only one neuron, and then it can be, for example, let me actually write it down. One neuron. It can be either regression problem, regression. You're predicting y hat, it can be any number or any real number, depending on what activation function you use, right? If I use a relu activation function for the output layer, I get numbers between 0 and numbers greater than 0. If I use a linear activation function for regression, I get any y's, right? But as I said, in practice, even the relu activation function just work fine, even for the output layer. If you have one neuron, it can be a binary class classification as well. So binary classification. Then if the output is multiple neurons, so for example, this is 2 neurons or 3 neurons, if this is the output layer, so let's say output, then we can have multi-class classification, so multi-class classification. For multi-class classification, we can use Softmax. So remember, for this one, we can use linear activation function, we can use relu activation function. For relu activation function, for binary classification, we could use sigmoid. So maybe this is a good summary. And then we can have another multi-label classification. So multi-label classification problem, classification. So if you're not familiar with multi-label versus multi-class, so multi-class classification, so for example, if I have 3 output, it can be, the output is one of them, right? So I use Softmax. The Softmax is going to give me, for example, this picture that you're showing me, is it a cat or a dog or a tiger, right? It's going to assign probabilities, and it's good that observation is going to be assigned to the to the class with the highest probabilities, right? So this is multi-class classification. What is multi-label classification? So we have some problems that you want to see in this picture. You know, I can see a car, a pedestrian, and a sign, right? And you're going to assign different probabilities to them. So this is called multi-label classification problem. And in the last layer, we usually do the sigmoid, because those probabilities do not need to add up to 1. Again, I want to say in this picture, there's 90% of seeing a car, 95% of seeing a pedestrian, and then 50% of seeing traffic lights, things like that, right? So this is called multi-label classification problem. Okay, so as you can see, we use different activation function depending on what do we have in the output layer. We're going to see all these things in practice in the Python and throughout the semester, so don't worry about it for now. So because sorry, because all the inputs are densely connected to all the outputs, these layers are sometimes called dense layers, right? So as you can see here, for example, you know, the input layer is connected to all the neurons. So we call them dense layers. Yeah, because they are all connected. Input and outputs are connected all to each other. Okay. And then one last thing I wanted to say is that the output layer can be either single output or multiple output. So we already talked about it. Single output, regression binary classification, multiple output, multi-class classification, and multi-label classification. All right. Okay, now let's talk about building a deep neural network, right? So far, what we have seen was a simple single neuron network. For example, in the housing dataset, housing problem, we saw that we can have, let's say, 3 inputs. It can be square feet, number of bedrooms, and I don't know, location. And then we're going to feed it to a single neuron. You know, these are the inputs. And then we applied an activation function. Let's say we did it in this neuron, right? It has a linear mathematical formula, and it has a nonlinear activation function. And then we generated an output, right? So this was our output layer. Basically, this is the y-hat, right? So this is a single neuron network, which is the simplest, or single perceptron network, which is the simplest neural network we can imagine, right? Now we said that if the output, you know, the output can be, you know, if we apply the, let's say, relu activation function or linear activation function, we can think of it as a simple linear regression problem, or I could easily put a sigmoid activation function at the very last layer and call it nothing but a logistic regression, because this is literally the logistic regression, right? So what makes the neural networks unique when it comes to getting better performance for predicting the the outcomes in the test set or cross-validation set is that it's the idea of putting or connecting hundreds or thousands of these nodes and stacking in multiple layers, sometimes even hundred number of layers, right? So this is where the name deep is coming from, right? So the deep neural networks are networks with large number of layers, and this is what gives them power, because if you have so many of these neurons, so many of these layers, literally any functional form can be approximated by this network. So you can imagine this is a, I don't know, this is a relatively large network with, let's say, in first layer we have 6 neurons, second layer we have, second hidden layer we have 100 neurons. Here we have 500 neurons, 200 neurons, 50 neurons, and an output layer, right? So, and this is a fully connected, the layers are all dense layers. So you can imagine any kind of feature engineering can be done under the hood, right? And it's the cool thing is it's all automatic. So any kind of relationship between these variables is gonna be explored through this dense network. So what I mean by that, so for example, you know, if you go 2 layers in, or if you go any kind of linear combination of these features are going to be explored in the next layer. And if I go to the next layer, it can, and if I add the nonlinear activation function, any kind of nonlinear complex pattern can be explored with this deep neural network, right? So as you can see here, the deep neural networks can learn and model very complex patterns. So this is the power. This is the power of neural networks, right? Especially in the train set, you can literally approximate any pattern in the data, and you can get an accuracy close to 100% in the train set. But we know that it's of course overfitting, so we have to use some techniques like regularization, like cross-validation, like data augmentation to make sure that the model is not overfitting. Okay. We know that DNNs have been successful in a wide range of applications, including image recognition, speech recognition, natural language processing, and machine translation. Okay, so again, this is the idea of deep, and the term deep is coming from the fact that we have multiple layers. So there could have been other names for this model, maybe layered representation learning or hierarchical representation learning as well. So the model is going to learn the pattern in the data in a hierarchical manner. So maybe in the first layer it's going to learn something, in the second layer it's going to learn something, and it's going to keep add up to that. Okay, so how do we do it in Python? Again, in this course we're going to use TensorFlow, and here is just if you use the sequential approach of deep learning. So I'm going to talk about these different approaches, sequential approach, functional API, and literally writing the subclasses based on the Keras models, right? So there are different ways, but the most simple one, and of course the least flexible one, is the sequential approach. But I just want to show you that it's super simple. We can build this, for example, network just as simple as this. From Keras we're going to work with sequential class. These are, and then we're going to, let me use the right pen. And you're going to simply keep adding layers to that, right? So we're going to say, okay, from layers, let's add a dense layer. This is our first layer, which is an input layer. Sorry, this first hidden layer with 6 neurons, and then the activation is relu. Then on top of this, we're going to simply keep more layers, right? So this layer with 100 neurons, this layer with 500 neurons, this layer with 200 neurons, and this last hidden layer with 50 neurons, and the very last output layer with 2 neurons, right? So as you can see, here we have 2 outputs, so we can think of it as a multi-class classification. And the reason that I'm saying that, because I'm looking at the activation function. If I'm using the activation function sigmoid here, this means that we are doing some multi-label classification, right? So we can have, I don't know, again, imagine this is image recognition. We want to see if in an image there is both car and pedestrian, and we're going to assign probabilities to those things, to those outcomes, and those probabilities do not need to add up to 1 necessarily. So that's why we're doing a sigmoid activation function. Don't worry about the details in these examples. We're going to cover them all throughout the semester and through using Python. Now let's talk about how do we train this neural network, and how do we train this deep neural network that we just talked about. So at the heart of it, there is this algorithm or process, you may want to call it, backpropagation. And so the idea is that to train a neural network, we're going to throw thousands or millions of observations to the network, and the network is going to adjust the weights and biases so that it can accurately predict the outputs from each example, right? And it's going to do that by minimizing the loss function. So each observation is going to do a forward pass, right? Forward propagation going from input level to output level. And then we are going to construct a loss function which is a distance between actual values and predicted values, a measure of distance between these two. And then we're going to minimize that loss function by going back through the network. So this process is called backpropagation, by adjusting the weights and biases. Okay, so as I said, this process is called backpropagation, and it's done using an optimization algorithm such as a stochastic gradient descent, right? So we have a loss function, and we're going to change the weight such that we go down in the gradient surface. So the loss function, again, as I said, it's a measure that quantifies the distance between actuals and predictions. So basically, it provides feedback to the neural network. There are so many loss functions that we can use for regression, classification, probabilistic regression, and etc. So for example, we can use mean squared error for regression. We can use binary cross entropy for binary classification. We can use, for example, categorical cross entropy. So these are the most commonly used loss functions. So for example, categorical cross-entropy is used for multi-class classification, but the classes are one-hot encoded, right? So for example, you have 4 classes that you want to one-hot encode them. It can be different colors, different animals, if it is image recognition, different departments, you name it, we have different classes. And for example, in stock, it can be buy, sell, hold, but you want to one-hot encode them. If you one-hot encode them, we are going to use categorical cross-entropy. But if you have a multiple class classification, which the outputs are digits, integers, we can do sparse categorical cross-entropy. So example could be, handwritten image recognition, right? So for example, you want to do using MNIST data, you have numbers between, let's say 0 to 9, so we have 10 digits, so we're going to end up with 10 outputs, and each of them is digit. So the loss function for that problem is going to be sparse categorical cross-entropy. All right, again, the list is very extensive. You can look at the Keras documentation, and it's well documented, and I highly encourage you to take a look at that documentation at least once to see what are the available loss functions. You can define your own loss functions, if you're doing more flexible method for coding these things in TensorFlow. For example, you're doing subclasses, or you're using the functional API. You can definitely define your own loss function, but most probably the loss function that you're having in mind has been already developed, so you can leverage from other people's codes. Okay, now the next thing I want to talk about is the details of this backpropagation. Okay, so as we said, it's the backpropagation is an algorithm. It's a supervised algorithm because again, you have the labels and it adjusts the weights and biases to make sure that it's going to minimize the loss function. So here's some notation that you should be familiar with. So this W star is the optimal value for weights, and we're going to minimize this loss function. Okay, so this is our loss function, which is a difference between actuals and predictions. Again, we talked about this one. The whole point in machine learning and deep learning is to approximate this functional form, this pattern, not functional form, this pattern, because some of the models, many of the models are non-parametric, so we don't know the functional form, but we want to approximate to that unobserved pattern in the data, right? So these are the predictions, these are the actuals. So some sort of weight that's well, some sort of function that's going to connect these things we can use. Again, we said that we can have different functional forms, right? And it goes for n observations. Observations goes from 1 to n. Okay, so what are the steps? Let's follow the steps one by one. So these are the steps in backpropagation. Step number 1, we need to feed the input data through the neural network. So this is the feed forward part, right? To compute the output. So this is what we call the feed forward thing. So you have an input x, and then you're going to throw some observations, and again you're going to through the network from input layer to output layer, you're going to come up with some predictions, right? So this is your prediction. Now you have y, again the data is labeled, you have y and you have y hat. You can go ahead and construct your loss function. So this is step 1. Step 2, you're going to calculate the loss or error between the predictions and output. So this is what I already showed you, right? This is a step 2. And step 3, we're going to propagate the error back. So through the network using chain rules of calculus to calculate the gradient of the loss function with respect to the weights and biases. So what does that mean? So imagine I have this j of w, which is a function of weights, right? And I want to calculate the derivative of this j of w with respect to, let's say, weight 2. Let me use, let's say, red. Let's say weight 2. So how do I do that? So basically, this is what we're interested in. You want to see if weight 2 changes, what is its impact on the loss function, right? Eventually, our goal is to find what is the effect of weight 1 on the loss function. But throughout the whole network, we are gonna see what is the effect of all the weights throughout the network, right? So if I want to calculate, for example, the derivative of j with respect to w2, I'm going to use a chain rule. So I'm going to say it's equal to, round j round y hat. So this is one step back. And then round y hat round w2. So this is the second step, right? So this is if I wanted to calculate the effect of weight 2 on the loss function. if I want to go further back in the network, or in this case, go to toward the beginning of the network, so I have to use again chain rule to go all the way back. So again, what is the derivative of j with respect to weight? W1. I'm gonna do, let's use another color, maybe green here. I'm gonna do is equal to rho j rho y hat, rho z1, and rho z1 rho w1. So this is what we're going to use. This is called chain rule, right? So, and then that was step number 3. Step number 4, we're going to update the weights, right? So we're going to update the weights and biases using gradient descent algorithm. So I'm going to review, so hopefully you know what is gradient descent algorithm. If you don't, in the next slide, I'm going to quickly remind you what was that. But the point is that using gradient descent algorithm, we are able to adjust these weights such that this j function, this loss function, is minimized. Okay, and finally, we're going to repeat this process until the loss reaches to a level that we are happy with, right? So maybe there's a threshold, or maybe we get to a point that the loss is minimized. Okay, all right. So now let's quickly talk about this optimization part of the loss function, which is we said that we're going to use gradient descent, right? So here again, this is our loss function, and imagine we are dealing with networks with only 2 weights. So this is very simple, very simple loss function, which is a function of 2 weights, right? And then the goal is to minimize these loss functions. So this is our W star. So we can have different approaches, right? We can have gradient descent, stochastic gradient descent, or mini-batch gradient descent. Let's go over them one by one. The steps are all the same, but they're different in one part of these steps. So let's see what is that. So let's starting with gradient descent. So in gradient descent, we're going to initialize weight randomly. So right? We have to start from somewhere, right? So tell me, where should I start? I can start from here and then go find the minimum. I can start from here. So we're going to start from a random number, W0 and W1. This random initiation itself can be optimized, right? But let's say we start from a random point, so that's step number 1. Step number 2, we're going to loop until convergence. So what does that mean? So we are going to say that go ahead and compute the gradient for every for the entire data set. So this is a point that makes the difference between gradient descent, stochastic gradient descent, and mini batch. So I want you to pay attention. So if I go ahead and calculate this gradient with respect to weights using all the observations in the data set, right? So using the entire sample. So if you have a sample size of 1 million, 10 million, you're going to calculate this gradient for 10 million observations, the entire samples. And then you're going to take the average of that and then call it, this is the gradient, okay? Then now we know what is the gradient. The next job is to go ahead and update the weights, right? So we're going to update the weights by this formula. We're going to say that whatever the weight used to be, now go in the opposite direction of gradient with this learning rate, right? Why we go to the opposite direction of gradient? Because remember, this is gradient descent algorithm, right? So if my gradient is positive, I want to go the other direction. So for example, if you are here and you have a gradient, and then you want to make sure that you go down, you get to the, maybe this is a global optimal, right? I don't know, maybe this is a global optimal, you want to stop here, you want to get stuck here, right? If it is a local one, we are going to use another solver to bring us here, right? But the point is that whatever the gradient is, maybe in 2-dimensional visualization, it's going to be easier. If the gradient is positive, you want to go to the left. If the gradient is negative, you want to go to the right. So that's why we go to the opposite direction of the gradient. And then eta is our learning rate, right? So the learning rate also is going to play an important role in these solvers. We're going to talk about all these details in the Python part. But that's in a nutshell. How do we do gradient descent? So eventually we're going to find the optimal weights. We repeat this process until we minimize that loss function. So what I want you to pay very good attention is this part. This is what makes it different from gradient descent, stochastic gradient descent, and mini batch. So in step 3, in gradient descent, we use the entire observations. Again, if you have 10 million observations in a data set, you use the entire 10 million points to update the algorithm, right? So at each step, if you want to update the weights, use the entire observations gradients, we took the average, and then you calculate this formula, okay? Now, as you can guess, this process, first of all, can take time. Of course, it's going to be the most accurate one because you're exploiting the entire information that you have, and the gradient path is going to be more stable. But the problem is that it's going to take long, right? Especially if the data set is large. So as you can guess, what is the alternative? Don't use the entire data set, use some of it, right? So the next thing is a stochastic gradient descent. So a stochastic gradient descent is where, again, all the steps are the same, but when you want to update the weights using gradient descent, you don't need to pass the entire observations. You only pass one observation. Look at that. I have observation I. I'm going to use that observation, calculate the gradient for that observation, and update the weight, right? Only using one observation. As you can guess, this is super fast because you're using only one observation and update the weights. But the problem with this, well, let's call it an issue, not the problem necessarily. An issue with this is that the path to the global minimum is not going to be stable, right? It's going to be, for example, it can, let me actually show you something. Let's keep these things simple. Imagine we are here. If I use gradient descent, so probably I'm gonna converge to the global minimum like this. If I use a stochastic gradient descent, I may even start going to the wrong direction because again we're using one observation. We can go like this, and but all the way we're gonna eventually converge to this global minimum, right? And the point is that it's going to be super fast, but the path is less stable. And the last one, which is something in between, is called mini batch gradient descent, right? Or mini batch stochastic gradient descent. And as you can guess, we're going to work with a batch of data. This is most commonly used, right? Work with a batch of data, and let's say batch size B. And we're going to say that go through this capital letter B observations. That can be, let's say, instead of 1 million, it can be only 1,000. Use 1,000 random samples from the data and calculate the gradient for each of those samples, take the average, and call it the gradient for that batch. And we're going to use it to update the weights. Okay, so this is going to be something in between. The path is going to be more stable compared to stochastic gradient descent, less stable compared to gradient descent, and the time is going to be take something in between, right? So maybe again the path is going to be a lot more stable, so maybe something like this. All right, so that was the loss function, the loss optimization in a nutshell. Okay, now let's see why we should go beyond gradient descent or stochastic gradient descent algorithm. And the idea comes from the fact that, especially in neural networks, the loss function is not necessarily well behaved, right? It's not clean, maybe. So here's a visualization that you can see for a deep neural network loss function. This is a landscape of neural networks, right? And as you can see, there are lots of local minimums, and then we have to make sure that the algorithm does not get stuck in one of them, right? So the idea is that, for example, if I use simple gradient descent or stochastic gradient descent with a specific learning rate, with a classical learning rate as we know, if I start from here, I may get stuck here. If I start from here, I may get stuck here. So how can we go beyond that? How can we give it some push or momentum? Think of this as a rolling ball going down the hill. How can I give a little bit of extra push to this ball that can pass the local minimum and get stuck in the global minimum? So this is our optimal goal, right? So that's the solution. We're going to design an adaptive learning rate that can adapt to the loss landscape, right? So the idea is that instead of, at each iteration that we're going to update the weights, instead of looking at the current gradients, we're going to take into account a weighted average of the previous gradients as well, right? So this is called the concept of momentum. And based on these momentums, there are lots of other solvers that are used for deep neural networks, okay? So we can think of, Atom, AdaDelta, AdaGrad, and RMS-Prop. So maybe the most practically used one, or most commonly used one, is RMS-Prop. Maybe this is number one, and then Atom number two, at least as of today. Okay, so which one is the right one? So how can we choose the right solver? Well, as you might have guessed, there is no right answer, right? Just like the discussion that we had for activation function, the same story is here. Some activation functions work better than the others. and some solvers work better than the others, and it all depends on the nature of the data set that you're working with, that you're dealing with. There are lots of solvers already available that comes with the Keras API, and here's the list. For example, you can do stochastic gradient descent, RMS prop, atom weighted, add a delta, add a grad, add a max, add a factor, atom, and the last one, FTRL. So again, these are available ones, but again, in practice, so most probably we're gonna work with this one or atom. Okay, it's gonna do the job for us. Okay, so don't worry about this part. We're gonna see how we can exactly apply these things in Keras and Python. So before I wrap up this part, I just want to make sure that when it comes to the Python part, we are all on the same page, okay? So there are three ways that we can use Keras API, okay? The first one, which is the easiest one, is using the sequential approach. So sequential is basically a class from Keras API, and we are going to build model like this. We're going to borrow the layers classes from Keras, and then we're going to add layers on top of each other like this. So this is the simplest one, but it is the least flexible, right? So maybe this is appropriate for the beginners, and the reason is that it's not flexible. So maybe in practice you want to do something more flexible. You want to customize your, I don't know, sometimes loss function, your metrics. You want to customize your optimizer and things like that. If you want to do something like this, you have to go beyond sequential approach. The second one is using functional API. And the functional API is basically, it's just like, imagine it's as if you're playing Lego, right? You have access to every layer, you can customize them, and so it is a lot more flexible than a sequential one, but at the same time, it is not 100% customizable, right? Because you have to use some built-in functions and applications from the Keras that comes with the functional API, right? The third, so this is probably the one that you're going to end up using, either if you go to industry or even in academia. If you're doing light research, you probably are going to end up doing functional API approach. The third one is just subclassing, right? So subclassing from the model class in Keras API, right? So this way you have access to every function. Basically, you're gonna write those things on your own. You're gonna write classes, and you're gonna write functions. You're gonna put, for example, your performance metrics and etc. in a call function within these classes, right? So it's a lot more flexible. I can tell, if you want to do unique new PhD kind of research, and you want to make sure you can customize all these things, functions, and it's a lot more flexible. So this is a good news. The bad news is that you might make mistake, right? Because sometimes these models that you're putting together, it's going to become larger with multiple layers, so the chances that you're going to make mistake is going to increase, and you do not have access to some of the nice visualizations or maybe some built-in training steps or fitting steps. You may not have access to those ones. So I would say for this course, we're going to start with sequential. So in this chapter, in this module, I'm going to start with the sequential, because I just want to make sure that you follow the theory first, and then once you feel comfortable putting these layers together, we're going to move on to the functional API, because in the computer vision part of the course, in the sequential deep neural networks, or in the transformers, we absolutely need more flexibility than that sequential approach. Okay, and we will not consider talking about the subclass approach, because again, this is beyond the scope of our class. And as I said, what most probably you're going to end up in real world, in practice, is a combination of the two. And this is what you can mix and match, by the way, from all these three approaches. But usually people mix and match from these. You can write some simple sub classes, and then add it to this functional API approach, And this way you have access to all those built-in capabilities that comes with the functional API. All right, so if you did not follow the last, I don't know, this last part, don't worry about it. We're going to talk about the details later on. So that was it. That was part one. In the next part, we are going to talk about regularization techniques and basically see what is tensor, because we're going to, as I said, we're going to use TensorFlow or this Keras API, and we should be familiar with the concept of tensor. So what do we mean by that? Until the next one, take care.